So, as you guys already know, opposite charges attract and like charges repel. Something called Coulomb's law quantifies that attraction or repulsion. Coulomb's law says that the electrical force is equal to this constant K, which is 8.99 times 10 to the 9th Newton meters squared per Coulomb. Oh, whoops, per Coulomb squared. Sorry, that's quite a unit. Times Q1, Q2 over R squared. Q is the charge in question. So you multiply the two charges together and then divided by the distance between them squared. This should look kind of familiar. A constant times a product of two somethings over a radius squared. That looks pretty darn similar to Newton's law of universal gravitation. So the inverse square law, gravitational force functions on the basis of an inverse square law. So does electrical force. I think the fact that we see the same sort of pattern in multiple different kinds of forces, the fact that there is this pattern in multiple different kinds of force, I think points toward is evidence that there is a design, a pattern in nature that points back to a designer who came up with both of these, how both of these forces work. Just to give you an idea of where these are at, we want to just do this in there and compare the order of magnitude of the gravitational force and the electric force between a proton and an electron in a hydrogen atom, where a proton and electron are about that far apart. So order of magnitude calculation means you just plug in the powers of 10. So force electric, what do we have? We have K, which is 8.99 times, whoa, whoops, I just realized this says 19 to the 9th. That should say 10 times 10 to the 9th. That makes more sense. So K is on the order of magnitude of 10 to the 9th. Electron and proton each have a charge of 1.6 times 10 to the minus 19th coulombs. So that's about a 10 to the minus 19th times a 10 to the minus 19th over, they're 5.29 times 10 to the negative 11th meters apart. Oh, so that's over 10 to the minus 11th squared. So, if we do this, this is a negative 38th times 10 to the 9th is a negative 27th over negative 22. So that's 10 to the negative 5th is the order of magnitude of the electrical force between those two. The gravitational force is equal to G, 6.67 times 10 to the minus 11th, times the product of the two masses, and we can look these up. Mass of the proton, 10 to the minus 27th, and mass of the electron, 10 to the minus 31st, over the distance between them squared, which is again 10 to the minus 11th squared. And what does that give us? Well, this is in our numerator here, what is this? This is negative 58, 10 to the negative 11th, that's negative 69, over 10 to the minus 22nd, it's negative 47. So, what's the difference between these two? 10 to the 40th. The electric force is it's 10 to the 42nd, but whatever. Electric force is about 10 to the 40th times the gravitational force between them. And that's kind of a good thing. What this tells us is that when we get down to atomic scales, electric force is way, way bigger than gravitational force. The gravitational force is negligible. Even if we put in mass of the Earth and how far they are away from the Earth's center, it's still a lot smaller. And that's a good thing, because if gravitational force was stronger than the electric force, and then protons and adjacent atoms repel each other with a force that's much stronger than the electric force, or than the gravitational force, which is good, because if gravitational force was stronger, then our bodies would just fall into blobs, and we wouldn't be able to have atomic structures and molecular structures in our body. So that allows us to exist. So I guess God knew what he was doing when he put together the electric and gravitational forces. Just as a reminder, we talked about this back when we first talked about the gravitational force, but there are 4 fundamental forces as far as things are classified. The gravitational force, electromagnetic force, weak force, and strong force. And as we go up, these forces are important with bigger objects. Smaller objects, so when we're dealing with a very large scale, like the size of, well, not even that large, but the macroscopic scale, gravitational forces become the biggest. At the molecular and atomic levels, electromagnetic forces are more important. The weak force shows up at an atomic level. It has to do with radioactive decay, and the strong force is important at the subatomic level. It's the force between that causes protons and neutrons to attract each other, and so they can stay together in the nucleus. And then as we go this way, we have a weaker magnitude going to a stronger magnitude. And this may show up on the AP exam, just a sort of general idea of what the fundamental forces are. It's possible that those could show up. And on a macroscopic scale, most objects are electrically neutral. They have about the same number of protons and electrons, so then gravitational force becomes the dominant interaction. I have a bajillion protons and a bajillion electrons, so altogether my body is more or less electrically neutral, and so gravitational effects on my body are more significant than electromagnetic effects on my entire body. Here's just playing with Coulomb's law a little bit. 2 identical conducting spheres with charges 1.2 microcoulombs, negative 2.4 microcoulombs, placed 3.5 centimeters apart. The magnitude of force they exert on each other, well, electric force is K. And actually, I would recommend go ahead, take this value of K, 8.99 times 10 to the 9th, go ahead and store it as K. And then when you're doing your calculations in your calculator, you can just type K. 1.2 microcoulombs is 10 to the minus 6 coulombs. And we plug those numbers in. They're 3.5 centimeters apart. It's 0.035 squared. And we can type that into the calculator. It can be easier to type in if you separate your powers of 10. So I would type K times 1.2 times 2.4, and then go E negative 12 instead of doing 10 to the negative 6 twice. Doesn't matter that much. But we can see the magnitude of force is about 21 newtons. The sign of the electric force just tells us whether the force is attractive or repulsive. So if I plugged in negative 2.4, then I get a negative. That would tell us that a force is attractive. It does not mean it's in the negative x direction or negative y direction. It doesn't work like that. So just like with gravitational force, if you have a vector problem, you need to assign your positive or negative sign based on what direction the force is, and your reasoning, it's attractive or repulsive, so that means it's left or right or whatever. These conducting spheres are touched together. How far apart must they now be placed to exert the same magnitude of force on each other as in part A? Well, if they're touched together, then what happens? Well, I've got a 1.2 microcoulomb conducting sphere touching a negative 2.4 microcoulomb conducting sphere. What happens? Well, the charge splits. So 1.2 minus 2.4 over 2. Now they each have charge negative 0.6 microcoulombs. And the question is, how far apart must they now be placed to exert the same magnitude of force? So now we have that electrical force is equal to 0.6 times 0.6 over some distance squared, and then we can calculate what that distance would be. And square root. And so the distance they would have to then be apart is very small. Wow. So that probably isn't possible, because they would have to be 1.31 times 10 to the minus 7 meters apart. For that to happen, they'd have to be super small spheres to begin with. Atoms are about 10 to the minus 9th meters apart. So that's only 100 atoms apart. They probably have more than 100 atoms in the sphere. So that might be a prohibitively small distance, but oh well, that's just an example of the calculation. Here's another good one. Positive point charge 2.7 millicoulombs is placed at ground height. At what height above the charge would a proton be in equilibrium? Equilibrium. Okay, well, we've got a positive charge down at the ground here, and then we got a proton sitting somewhere up here. Well, what forces are acting on this proton? Well, we're going to have gravitational force downward. We're going to have electrical force upward. So for it to be in equilibrium, the electric force has to be equal to the gravitational force. So we can then plug numbers in and calculate 2.7 millicoulombs is 10 to the minus 3rd. The proton charge, 1.6 times 10 to the minus 19th. And the mass of the proton, 1.67 times 10 to the minus 27th times 9.8. And we can then calculate what distance apart they would have to be, or what height above the ground the proton would have to be. It might be very small. Excuse me. Or actually it might be very large. I was thinking backwards. Error syntax. What do you mean error syntax? Oh. I guess you can't do E-1. Wait, what? Oh, parentheses that don't have a match. Okay. And that's pretty big. So that, well, I guess that's height. Height above the ground would have to be pretty darn big. 1.54 times 10 to the, oops. 1, 2, 3, 4, 5, 6, 7.